Good morning, ladies and gentlemen, and welcome to NASA Ames Research Center. Today we are discussing the Lunar Crater Observation Sensing Satellite Mission, LCROSS, one of NASA's next steps to exploring the moon and our solar system. Today we are, the mission is going to announce the crater that has been selected as the optimal location for evaluating if water exists on the south pole of the moon. On the panel, we have Dan Andrews, LCROSS Project Manager, Tony Colprete, LCROSS Project Scientist and Principal Investigator, and Jennifer Heldman, Coordinator of the LCROSS Observation Campaign. After each has spoken, we will be taking questions from the news media. And with that, I hand you over to Dan.
Thank you, Jonas. Well, good morning, everybody. It's truly a pleasure to be here today. I thought I would open up with just a reminder of what the mission is and then give a status and go forward from there. So LCROSS is a lunar impactor mission. We launched on June 18th of this year with our sister mission LRO, the Lunar Reconnaissance Orbiter. And since then, we have been flying in a Earth orbit preparing for an impact on October 9th, coming up in just about 28 days. The purpose of our mission is to see if there may indeed be water ice located in some permanently shadowed regions on the south pole of the moon. The way we do that is pretty clever, actually. We take our spacecraft, the LCROSS shepherding spacecraft, and instead of separating after launch from the upper stage of the rocket that brought us to the moon, we hang on to it. And we use that as our impactor. And so we are right now dragging around in orbit around the Earth the upper Atlas V stage called the Centaur. And then on the day of impact, we will finally separate from that impactor. It'll be drawn into the moon by lunar gravity. Of course, the LCROSS spacecraft will be drawn in as well. We will slow down the shepherding spacecraft, so we give time for the impactor to go in. It will kick up whatever is on the floor of the crater. That may very well include water ice. That is the whole point of the mission. And kick it up into the sunlight so that we can monitor it. We have many instruments on the spacecraft that will be checking for its composition. And then finally, about 4 minutes after the first impact, the shepherding spacecraft impacts, and game over. We're done. So all that data that was taken was sent back to Earth, of course, live during those 4 minutes. Now, status of the spacecraft is good. We have been working very hard. This is a small, innovative mission, and pretty low cost as these things go. And so it's been a lot of work. We've overcome some challenges, but we, at this point, 28 days out, have every expectation of finishing the mission with full success. The LCROSS team, however, was in the July timeframe, in particular mid-July, was saddened by the loss of a notable figure within the exploration community. And of course, that was noted journalist Walter Cronkite. He was the face of exploration for many decades, starting in the early Mercury days, of course, through Apollo. We all remember seeing him on television during the Apollo 11, in particular, landing on the moon. And so this notable figure, who represented so much for the American public in making space exploration digestible, understandable, is someone that NASA and the LCROSS team would like to dedicate the LCROSS mission to. And I'm very pleased to see that Chip, his son, is here today. And I understand he would like to share some words.
Some very few words. It's a great honor. Thank you very much. And Dad would be very pleased to be part of this ongoing process. we find water so close. It's a attractive oasis for further exploration. So once you build that refueling station up there, or whatever it is, we'll come back and we can have another renaming ceremony then. Thank you very much, and good luck.
Thank you very much. I'm glad you could be here. So, with that, the reason we're here today is to talk about where LCROSS will be going on the moon. Today, as you've heard, we have the project scientists and principal investigator Tony Koloprit and Jen Heldman, who are going to be talking about the crater that was selected and how the impact will be observed. And with that, I'll turn it over to Tony.
Thanks, Dan. And thank you, everybody, for coming to hear where we plan on going. It's, I should say straight up that this has been a long process, actually, even before we submitted the idea, the proposal to do LCROSS. People have been thinking about this and considering where they would go and explore for water on the moon. Since then, LCROSS has been exceedingly fortunate to have a number of observations from a variety of observatories from the international community, including the Japanese mission, Selene, the Indian mission, Chandrayaan, and now LRO, the Lunar Reconnaissance Orbiter, our sister mission at the moon. These observations, plus those made from the ground, from radar observatories on the ground, have been instrumental in our understanding of where to go and have given me great confidence that we have picked the best possible site going forward. So with that, I'm going to show some video and some imaging of the process and the places where we've considered, and reveal to you the ultimate target that we are sending LCROSS to explore for water ice. So we can start the video now. The LCROSS mission launched in June of this year, and that really set the pole we had to go to. It's springtime in the southern hemisphere right now, and so we have good lighting. What you see in the video here is the lunar South Pole, a variety of craters down there that we had to consider. What we had to do over the last year and a half, 2 years, was pick one of these to go to. And what you see here are finalists that we've used Kaguya data and Chandrayaan data and LRO data to help us actually determine which one. Over the last 3 months in particular, LRO has been very active in observing these specific craters for us. What you see here is a radar image from the Goldstone radar dishes in California of the South Pole. You can see a variety of craters down there. We looked at such craters as Shackleton, Shoemaker, Hayworth, but they had to meet certain criteria, and I'll tell you what those criteria are in a moment. And the crater we finally selected is shown here now. It's Cabeus A. Cabeus A is at about 81 degrees south. It's a little bit off the South Pole. It's a relatively large crater, about 40 kilometers across. And as we zoom in and look at it here, you can see it has a rather large crater along its rim, and that is where we think the sweet spot exists. We're going to continue to refine our understanding of this crater now that we've selected it with detailed observations from LRO, and continue as we get closer and closer to impact, refine the exact position within this crater that we are going to impact. We already have a very good idea where it is, but we have the fortunate ability to refine that in the next couple weeks. The next image here shows the topography of this crater, Cabeus A, as seen from the Goldstone radar dishes in California. Yellow is low, blue is high. Topography is really important because it really determines the illumination within the crater. Sunlight is blocked by topography, and you can see here the black areas are actually shadows cast by the radar. The topography is blocking the radar signal, and we see it as shadows. The sun does the same thing. So really important to the LCROSS mission success is to get the ejecta, the dirt that's thrown up out of the crater, into sunlight. And that's what we want to do, is get dirt into sunlight. So that was one of the principal aspects that we looked at in terms of selecting a crater. This also affects the Earth observability. How observable is the ejecta and the impact from Earth? And I'll comment on that a little bit more later. Also from this topography like this, and topography that we got from the Selene mission and from LRO, is slopes and roughness. We want to hit a nice, flat, fluffy place. The more flat, the fluffier it is, the more material gets thrown up in a very predictable way. If we hit on angles and slopes or blockiness, that affects the ejecta and how it flies upward in unpredictable ways. So we want to avoid that. What you see here in this graphic are slopes derived from that altimetry, that topography image you just saw. Blues are low slopes. These are slopes of just a few degrees, less than 5 degrees, whereas the yellows and the blues are slopes as much as 20 or 30 degrees. We want to avoid those steep slopes. Luckily, in most of the craters we looked at, we considered, they had large, flat, even floors. And the data we've looked at, even at scales as small as 40 to 50 meters, we've been able to find areas that are relatively smooth, boulder-free, and flat. We're using image data from the terrain camera on Selene and from LRO to actually see down into these craters using just scattered light, just earthshine light, and be able to pick out individual boulders that we want to avoid. So the process is ongoing, but we've been able to find very good candidate target locations. Specifically to this crater, Cabellas A, the conditions look very ideal. One of the more important criteria, of course, is its potential association with water ice. We don't want to go someplace dry, even if it throws up a lot of material. So how do we know if a place is wet or dry? The data that we have, the most reliable data, is neutron data. Neutrons are emitted from the moon. By observing how many neutrons come up from different places on the moon, you can determine if there's hydrogen there. And this is really one of the first clues from Lunar Prospector over 11 years ago now that there was potentially water at the poles of the moon. There have been detected hydrogen concentrations at the poles of the moon, and that's really what we're using as a guide to selecting crater as well. Lunar Prospector's observing footprint, the resolution of the data it took was very coarse, 40 to 70 kilometers. The LRO instrument has much higher resolution. It has 10-kilometer resolution. That crater I showed you was about 40 kilometers across. It's about 60 miles or so. The footprint that LRO can see, measure neutrons, is about a third of the size of that crater or a little bit less. So we can actually tell where in that crater the hydrogen is piled up, so to speak. We can also use analysis and look at older data sets from Lunar Prospector to really understand where the hydrogen is, assuming certain things about its potential distribution. This graphic here shows some analysis that has been done by colleagues on our science team on LCROSS, showing the potential water ice concentration in the craters that I've just discussed. The color coding indicates the potential concentration of water, blue being about 2% water. That's a significant amount of water actually for the moon. The gray area is the topography of the moon, and you can see Cabellas A, our target area, circled there, and we can actually zoom in on that a little bit, and you can see that dark blue dot there. That's in that large crater to the edge of Cabellas A. That's what we're really looking at and considering right now as what I called our sweet spot. That's really where we think we need to go. You can see this analysis suggests there's quite a bit of water in there. It is consistent with observations from Lunar Prospector, from LRO, the neutron measurements from LRO, all indicate that there's quite a bit of hydrogen in this area. LCROSS wants to understand what that hydrogen is. So the last criteria really is observing from Earth. We wanted to make a very robust observation campaign and have multiple assets looking at this. You're going to hear more about this specifically from Dr. Hellman in a second. But in terms of selecting a crater, we had to make sure it had good observability to Earth. And so the next movie will show some observations that were made about a month ago from one of our collaborators in New Mexico. This is from the Apache Point Observatory. These are colleagues from New Mexico and Marshall Space Flight Center who made these observations. This is with a camera on a 24-inch telescope, and you can see Cabellas there, Cabellas A shown circled. It is very observable from Earth. This is again one of the reasons we selected it. It gets good illumination and is very observable. We'll have lots of assets looking in this region during the impact. So we'll have lots of eyes on it. So with that, and to expand on that, I'll hand it over to Jen, and she's going to tell you about the observation campaign.
Great, thanks, Tony. So thank you very much for the opportunity today to give you a brief update on the observation campaign. And as Tony has mentioned, we have a very robust observing campaign that's currently underway. And the overarching philosophy is that we would like to have as many eyes and instruments watching these impacts as possible, because this is the way that we will get the most data and the most information from this unique lunar impactor experiment. So to that end, we put together a great team of astronomers from around the world that will be using our greatest telescopes both on the ground and in space, and I'll give you an overview of some of those, and to try and get as much data back as we possibly can. And our working philosophy within the observation team is one of cooperation and collaboration. So we have taken these astronomers and we have folded them into the LCROSS science team, and they have become a part of the LCROSS project. And by doing this, as having them official parts of the actual project, we're able to work closely together with the astronomers to help them in the planning of their observations and securing and observing time on these large telescopes. So we're able to work together. We're working together now in the pre-planning phase, and Tony just showed you one of the maps from New Mexico State and Marshall Space Flight Center, where we have mapping so that we can see where the craters will be, targeting, pointing, information regarding the impact sites, dates, times. So all of these details are all being worked very closely within the team. So I'd like to give you just a brief overview of some of the observatories that will be watching for LCROSS. So if we have the first graphic that comes up. Here's just a sampling. There are 6 actually represented here. In Hawaii, we have the Keck, the Gemini, and the IRTF, or the Infrared Telescope Facility, that will be observing the LCROSS impacts. In New Mexico, we have the Apache Point Observatory, and also MRO, which is the Magdalena Ridge Observatory. And out in Arizona, we have the MMT Observatory. And these are all very large, professional scale telescopes that we'll be observing. If we go to the next graphic, you see here are some locations of some of the other additional observatories. We have more, but the point is that you notice that they're clustered in the western United States and then out to Hawaii. And there is a strategic reason for this, and that's because these are the locations on the Earth where LCROSS will be observable during the time of impact. So for these astronomy observations, you have to be in the nighttime, so it has to be dark out. And so on the eastern coast, on the east coast of the United States, it'll be 7:30 a.m. on October 9th when we impact. So the east coast will have just seen daybreak. So you need to be from essentially the Mississippi and westward, still being in nighttime. So it'll be 4:30 a.m. Pacific time here in California, so still well in darkness. The moon will be up, and so these are the prime locations on Earth where the observations of the actual impact event itself can take place. If we go to the next slide, there are, in addition to the observatories that we have on the ground, we also have several space-based assets that we'll be observing. In Earth orbit, we have the newly refurbished Hubble Space Telescope. We'll be observing the LCROSS impacts. We also have Odin, which is a Swedish radio telescope, which is trained for looking for water vapor, so they will be observing. GeoEye will be operating their ICONOS satellite out of Colorado, and they will be turning towards the moon at the time of impact to collect observations. And then the Earth Observing 1 satellite will also be looking at the moon, collecting observations, and then sharing those with the LCROSS science team. In addition to Earth orbit, we also have the Lunar Reconnaissance Orbiter, or LRO. And as been mentioned already, LRO is our sister mission, and LRO has been helping us both before, during, and after the impact. So pre-impact, we've been doing a lot of site selection work and collecting the data and analyzing the data in conjunction with the LRO team that Tony has already talked about. LRO will be observing during the impact event itself, and then LRO will still be in lunar orbit, so they will be doing post-impact characterizations and following up, taking observations of the impact site after the impact event. So in addition to these space-based and the ground-based professional assets, I'd also like to mention that we are mounting a very large amateur astronomer campaign. We expect that the LCROSS impacts will be observable in 10 to 12-inch telescopes, and so we are actively soliciting observations from the amateur community and encouraging folks to go out in their backyards, planetariums, science centers, collect observations of the impact, and then send those into NASA. And we are imminently launching what we call a citizen science website, where we will be collecting observations where people, amateur astronomers, can go out, collect their observations of the impacts, and send them into NASA, which we will actually use within the science team. So we think that we have a very strong, robust observing campaign that's underway. We're currently doing work now, and it's timely having this press conference now because we are about at the same phase, the moon is at the same phase now as it will be at impact. And so this is when the moon looks most similar to what it will look like on impact night. So we have several teams that are out collecting pre-observations and practicing their pointing techniques. And so we're getting a good sense of what we'll be able to observe, and now we have the target crater. So with that, Dan?
Thank you, Jen, and thank you, Tony. So we've got an exciting mission here. This will not only service the scientific need that we're trying to figure out, which is the presence of water on the moon. Is it there? But you can see there's a lot of good public engagement on this. I know my kids and everyone else's kids on the team and around the viewable public are going to be having viewing mornings. We're going to have that throughout NASA. It's going to be very exciting. So as a quick summary, we've got about 70 days behind us, about 30 days in front of us, roughly, before impact. And stay close, watch us on the web, watch us through your own telescopes, and watch this exciting mission. Back to you, James.
Okay, thank you very much, team. And so what we'll do now is we'll be taking questions locally first, and then we'll take remote questions over the phone. We have two mics on the floor, my colleagues Sheila and Mike. If you have a question, please flag them down and they will bring the mic over to you. Okay, before asking your question, please state your name and affiliation. Okay, with that, we'll take first questions. Okay.
I'm Dave Perlman from the San Francisco Chronicle. Talk a little bit about the degree of resolution that LCROSS has and LRO have as to so you can precisely and how precisely you can pick out the final target.
Sure. It's the resolution, so there's a few resolutions. There's a resolution of our understanding where we should go. That has increased dramatically over the last year. In terms of actually understanding where the hydrogen is, we won't know that to better than 10 kilometers. That is the best resolution we can hope for. Now, there is a radar on LRO called Mini-RF, and it can detect high concentrations of water down to less than 100 meters. So it has the potential of detecting pockets, small pockets of water, and we are certainly looking at that data with respect to these target sites. What we can actually achieve from a capability standpoint is our science team is using approximately a 3-kilometer circle, meaning we are very confident, very certain we can target within a 3-kilometer circle anywhere on any of these targets. Our most recent performance looks like it's going to be much better than that, but we have not found any place that we had to have that kind of performance, meaning we can identify places that are smooth, flat, and associated with hydrogen at scales of 3 kilometers. So we're very confident we'll hit a good place. Whether or not the hydrogen is distributed at very small scales, that's a question LCROSS is out to answer. So this is really what we're going to find out. We'll never be able to detect with any technique right now in orbit exactly what the smallest scale distribution is. LCROSS is the first mission that will be able to give us any kind of clue as to if it's distributed broadly or if it's distributed in small pockets. And as I mentioned, between now and up until October 6th, even the day of impact, we'll be trimming our trajectory just right so it gets right on the spot. And we'll know the impact time to a second.
Okay, next question.
Hi, Matt Bigler, KCBS San Francisco. How soon after the impact and after you've observed some of these shots will you be able to determine if there's water there?
Really depends on how much water it is we hit. You can imagine if there's a lot of water, its signal will be very strong in our instruments. The LCROSS mission is a unique mission in the sense that with regards to the instrumentation and the measurements, we never do anything more than a couple times. We swung by the moon, we turned on all of our instruments once. That was kind of a preparatory for impact. We've had several Earth looks where we look at the Earth and the moon and we practice and calibrate our instrument techniques. So what we've developed is really a real-time processing routine where as soon as the data comes in, we're able to real-time process it and turn it around very quickly. That's kind of been a requirement in our mission. We will be able to look at this data immediately afterwards and comment on how successful the experiment was in terms of, did we get a good ejecta cloud? Did we get the kind of signal we need to answer the questions? And that's exactly what we're also going to get from all the various observatories. I suspect we're going to want consensus between several of the co-investigators before we make any kind of statement with regards to water. It is a fundamental question, and we want to be very careful and certain about our declaration depending on the outcome. So very quickly we'll know if the experiment was a success within an hour. Really, real time. People will be able to participate, watch the impact, watch our video. We're streaming the spacecraft video live, so everyone can actually see it as we see it. And so I think we'll all know how successful the ejecta curtain was in forming. But then we will comment, the plan is a couple hours after impact, comment on exactly what we saw. And from there on out, we have a requirement to report to NASA within 3 months regarding the presence of water at the pole of the moon.
Okay. Do we have any other questions here in the audience? Okay, we have one over there.
I'm Haruna Kimura, NHK Japan. You had a fuel problem earlier. Does it affect sending a rocket to target accurately?
I believe you're speaking about the anomaly we had a few weeks ago. Dan can comment on that, and then I think you could probably comment on the effect to accuracy too.
Yeah. So couple weeks ago, thereabouts, we had a fault condition that was noticed while we were out of view. Now, I should back up and point out that LCROSS is not in continuous view of Earth assets. That was by design. We have shifting that goes on, and we look at the spacecraft on a certain periodicity as part of our normal plan. During one of those times when we were not viewing, and in fact we're out of view, we were in the southern hemispheric area of the orbit, so we were out of view of any assets. An anomaly on one of the avionics elements caused us to switch modes into a pretty costly propellant consuming mode, meaning we were using a lot of gas, if you will. And when we came back into view, that was immediately apparent. And we were able to confirm it 2 or 3 different ways within a minute or two. So we immediately took an evasive maneuver, if you will, and resolved the problem, stopped the propellant burn. So we took care of the situation, and then we had to figure out, okay, so what are we going to do through the rest of the mission? And so for the past 2.5, 3 weeks, we've been slowly, carefully adding additional controls in place on the spacecraft to make sure that this doesn't happen again. We've actually retuned the control system because we had a relatively large propellant margin. We were carrying a lot of extra, and now we're not carrying a lot of extra. We still have enough to finish the mission with positive margin, but now fuel efficiency is incredibly important. And so we have basically redesigned the control system tuning to really sip on fuel, to barely use any fuel, and have propagated that forward through the completion of the mission. And so as I said in the beginning, with that propagation forward and with our controls that we have in place, we believe that we can finish all of the mission objectives that we set out to. We've just had to retune things to make sure that that's the case. With respect to our targeting accuracy and the trajectories, what's interesting about what happened was the spacecraft did fine from the standpoint of navigation and the trajectory. We never went into a tumble, we never went out of control, everything was fine. We were just consuming too much propellant through that period. So when we came into view, the spacecraft was pretty much where it should be. And so there was not a consequence, if you will, to our targeting accuracy. In fact, that's validated by the fact that we had scheduled several TCMs, trajectory control maneuvers, across the whole mission by design. And we've actually been turning them off, not doing them. And not as fuel-saving measures because we don't need to, because we're within the error band of where we needed to be. And so we just are not going to hold a burn there. And I think there's now been 3 of them that we've canceled, one of them being even since the anomaly. So we're doing great on the trajectory.
Yeah, the one that was canceled, this last one that was canceled, was our scheduled retargeting burn. But we were so close to on target as it is, we didn't need it. It was, we launched targeting Cabeus as our prime, but knew we could change up to 30 days prior to impact. So yeah, as Dan said, we're right on target.
Okay. Do we have another question here in the audience? Okay. We have some calls, some questions from on the phone. Our first one is from Irene Klotz from Discovery News. Go ahead, Irene.
Hi, thanks very much. It's Irene Klotz. And I have a question about the overall chances of mission success. I know it's a very low-cost flight, and with the added, I guess, eating into your fuel margins, if you have some sort of realistic assessment of your chances that this is all going to work out the way you want it to. Thanks.
You bet. So what we did after we had gotten everything under control and in nominal condition again, was we set out and said, all right, what is the uncertainty that we have with how much propellant we have left, right? You don't have a float in the tank. You have to figure out how much propellant is left based on the temperatures and pressures and so forth of the tank. You even have to take into account how much propellant's in the lines. As you know, with your own cars, you can have fuel in the lines, but if you don't have enough pressure to deliver it, you'll start sputtering and run out of fuel. So we've tried to take into account all of those little features of our spacecraft, held a little independent review. And so we have a uncertainty band on how much propellant we have left. And even if you were to take the worst case uncertainty, where it's absolutely the lowest possible number, we still have positive margin to finish the mission as designed. So we feel pretty comfortable that we actually have enough to do it. Does that answer your question?
No, actually, I was more interested in, I mean, there's a bunch of other things that need to happen. You need to be able to separate from the upper stage. You need to, there's just a course of sequence of events that need to go exactly right. And I just wanted to know what you think your overall chances of mission success are.
So we did factor into our assessment all those things: the braking burn, the remaining trajectory control maneuvers, the TCMs as we've referred to it, and Earth stare where we're doing another calibration. All those activities are all laid out in a timeline, and there's a cost, a propellant cost associated with each of those. So those are all factored in. As far as assigning a likelihood of success, we don't have a number associated with that. We know that we have enough margin, even under this worst case scenario, that if other things were to go wrong, if one of these maneuvers that we did were to be more costly in propellant than we had figured, we have margin to account for that. And so I think what we've basically done is lost the great deal of excess propellant that we had at time of launch, and now we have enough plus margin to finish it. I hope that answers your question.
Yeah, one thing I could add to that was there were specific launch dates that we considered green, meaning go, with essentially the same kind of margins we have now. So I don't think we're actually in any particularly worst case. If you actually stuck back and ignored the anomaly, This is a unique mission in that it was a Class D mission. It was inexpensive, done quickly. But to this point, things have worked out incredibly well. So I'm very optimistic and that things will continue to go well. Problems always occur, but the team is incredibly sharp, experienced, and performing incredibly well. The fact that we added in an Earth calibration stair on the 18th of next week just kind of shows, I think, the team's confidence that things are going according to plan.
Thanks. Who just spoke?
This was Tony.
Thank you.
Sure.
Okay. Our next question is from Ron Cohen of Science News Magazine. Go ahead, Ron.
Yes, I wondered how long the plume would last and how long it would be visible for amateurs, and then, how long it might be visible for bigger telescopes.
Sure. Good question. It's a relatively short event. It will be visible from our vantage point from the get-go. The LCROSS spacecraft, of course, has the unique vantage point of being directly over the impact and coming in fast towards the impact. We actually get to fly through the remnant vapor cloud, imaging the crater the Centaur made all the way down to, we expect just several seconds before we impact ourselves. So we'll just be 25 kilometers or so, just 40 miles above the surface before we actually lose comm from our spacecraft before it impacts. The actual duration of the ejecta cloud, where it is visible by most assets, including ground-based observatories and amateur observatories, is about 90 seconds. It will be its brightest in between the 10 to 60 second time frame. It will be from the ground, from the Earth. We anticipate it will be approximately a magnitude 5 for those astronomers out there, which is quite visible, even maybe as bright as magnitude 4. So it should be, and that brightness will last about 30 seconds or so before it slowly fades away as the ejecta cloud settles back to the surface. Hopefully that answers your question.
Yes, thanks.
Okay. We have another question from Paul Taylor, Globe and Mail in Toronto. Go ahead, Paul.
Hello. If the craters that are in the shadow do contain water might they possibly contain? Like, I'm just asking you to basically ballpark it based on the size of the craters. And can you give us some kind of comparison of how much water that might be? Like, might be the same amount of water that's in Lake Erie or Lake Ontario? And I know this is just pure speculation, but how much might be there in the best case scenario?
I think I caught most of your question, is how much water could potentially be in this crater where we've selected, and give some kind of real comparison. I once did the math with a lot of assumptions. Like you said, you have to make a few assumptions, but if you took all the areas that are shadowed on the moon and you assume the top 3 feet or meter of that material contained 1% water ice, it is I worked it out using the Great Salt Lake, which I've had a lot of people criticize me because Great Salt Lake changes its level quite often. It's about 3% or so of the Great Salt Lake's water. As you saw in my presentation, we think potentially in some of these regions you could have several percent water. There is some radar indications that may be that in some locations you have much more water than that, and that's, so it could be substantially more. You are talking Lake Erie kind of volumes if the water actually extends below a meter. And why I say a meter, why I say 3 feet is because the neutron measurements only can detect hydrogen to that depth. They don't know, we really don't have any idea, except through theory, what could exist below that depth. There's every reason to believe that if there's some hydrogen and water in the top meter or so, there's probably some below that too. So those are probably lower estimates. The new data sets from LEND and from LRO in general, the instruments on LRO will really help us understand what the global distribution is on the moon. Likewise then, LCROSS ground truths that measurement. We actually go to one of these places, lift it so we can observe it, and so you can really say what that means in terms of, like you said, how much water is really there. So, ask us again about 30 days after impact, and I think we'll have a much better idea.
Okay. We don't have any other calls from remote calls, so I believe we have another question here for Mr. Perlman.
Hi, it's Dave Perlman again. Tony, the big question, I think, a big question, is why water? Why do we want water on the moon? And I'm thinking particularly, and this is maybe tough for you, I'm thinking particularly of the recent panel that suggested that maybe we should defer our human landings on the moon.
Right. Well, I can certainly answer your first question. I'll probably wave off the second question because that's a policy question beyond what my job entails. But I think the first question will actually dilute your second question. Why water on the moon? First of all, we know it's hydrogen. It could be other compounds. It could be water. It could be methane. It could be hydrocarbons or organics. And so actually from a scientific standpoint, this is incredibly important. Whatever the moon has collected over the last 3.5 billion years in terms of water, organics, materials from comets, asteroids, from the sun, could be trapped in these pockets on the moon. It's a time capsule. It's a window into the past of the entire inner solar system of Earth. So I see LCROSS really and LRO combined as a gateway, a pathfinder towards truly understanding even the origins of volatiles, of water in the inner solar system. The moon is right there. It's right next to us. We can go there much more easily than a lot of other places and make these studies. And so that's why it's incredibly important to make these studies. Water in terms of exploration is very important. Even if we don't go back to the moon, it is a principal resource throughout the solar system on Mars, for Mars exploration and beyond, quite frankly. So, the old Mars mantra was follow the water. And really that extends, in my mind, through the entire solar system and the entire universe. And so really LRO and LCROSS are the first steps and directed, focused steps in that direction towards the moon. Hopefully that answers your question.
Okay, do we have any other questions? Okay, seeing no other questions, this wraps up the LCROSS media briefing from NASA Ames Research Center. I would like to thank our panelists and our special guest, Chip Cronkite, for their time today. For more in-depth information about the LCROSS mission, please visit www.nasa.gov/LCROSS. It's on your screen at the moment. And thank you very much for joining us, and we look forward to seeing you again on October 9th. Thank you.